together. I'm the PI of the, I'm the principal investigator of a NIH-funded Center for Biomedical Technology and Research, the goal of which is to develop and share with you, disseminate new technology. So we're going to talk about molecular modeling and simulations, as you know. And there are essentially two groups of software we are going to talk about. In the first 2 days, it will be about what's called PRODI. We pronounce it PRODI. And in the second half, it will be about NAMD and VMD. PRODI is a software based on elastic network models developed here at the University of Pittsburgh in my lab. And NAMD is a molecular dynamics software together with its visualization tool, VMD, at the University of Illinois Urbana-Champaign. So I'll give you a brief introduction about the overall workshop plan, introduce a few people, and then I would like to also know who you are. We can do a brief introduction around the room. Let me start with the, can we dim the lights here? Do you know how to? So let me, this is organized by two different centers currently funded by NIH. So let me see. Okay, great. Thank you so much. Looks good. One of the first is the TCBG, which is at the University of Illinois Urbana-Champaign. And the second, MMBioS, or Multiscale Modeling of Biological Systems, is here. Okay. So I would like first to talk briefly about the TCBG, which has been founded in 1989. I would like to take this opportunity to pay tribute to the founder, Klaus Schulten, whom we lost last year. He was one of the pioneering scientists in the field, the leader of the team that developed NAMD and VMD. NAMD is the molecular dynamics software, which will be the topic, the center of the second half of the workshop, which has been cited more than 9,000 times to date. So that shows really how it is broadly used. And VMD, the visualization software, is even more broadly used. You could use it together or independently from NAMD. Klaus Schulten has been leading this effort for several decades. Now he has his successors who are continuing, and we will have one of them, a leading scientist again in the field, Professor Taksh Khorshid, teaching in the second half of the workshop. And this is a little bit about our center. This is a joint effort between Carnegie Mellon, Pittsburgh, University of Pittsburgh Supercomputing Center here, and the Salk Institute for Biological Studies at San Diego. So it is the goal of our center is to understand better the spatial organization and temporal evolution of complex events, biological events, with focus on synaptic signaling and regulation. So within the scope, we are building new tools, new software, from molecular all the way to cellular, and even all the way to organ level. And the main organ is brain in our case. So if you see here, you can see how the dimensions, we're talking about nanometers here. This is the type of calculations we do at the molecular level, and PRODI, as I mentioned, is a major tool. At the cellular level, we have this Monte Carlo simulation software, and the main developers, Terry Sinofsky and Tom Bartol, are from the Salk Institute. And here's our workshop. We have another one, actually, upcoming in 4 weeks on the use of AMSAL. Now, the instructors, as I mentioned, we have Emad, who will be teaching in the second half of the workshop. He's a professor of biochemistry and pharmacology and biophysics and computational biology at the University of Illinois. And I'll be teaching the first half. Now, the two centers have, you may have already met with Alex, who was here. He's at the PSC, Pittsburgh Supercomputing Center, in charge of training and dissemination activities of our center. Joe Ayub is at the University of Pittsburgh. He's also in charge of leading these efforts. And Joe Ribeiro is from the University of Illinois. Alex has been very involved in many training activities, especially for minority serving institutions. Here's a photo of him. And Joe is equally busy, actually. He organizes all the summer courses, summer programs. And this is a photo from our Tech Bio students who are also around right now. Undergraduates from all the United States universities, usually visiting us for 10 weeks. So that is to learn about computational biology. And I would like to introduce the assistant instructors as well. Jihan is there in the back. And then we have James, also I saw him. Jiang is there. And from the University of Illinois, we have Dr. Pawin. Pawin is good? Okay. And also we have Jiu. He's a PhD student. So we have a mixture of PhD students. And is there anybody whom I didn't list here? I think the other members are not here right now. But this will be during the afternoon sessions. They will be helping you. So John just came in. So he will be also serving as an assistant instructor. He's a PhD student in our PhD program between University of Pittsburgh and Carnegie Mellon University, a joint program in computational biology that we are offering between the two universities. So here's a brief outline of the program. As I mentioned earlier, we have the first 2 days. It will be on collective dynamics on proteins, and also the extensions, the several applications, including understanding sequence properties, druggability simulations. And in the last 2 days, Emad will be teaching not only NAMD and VMD, but a new extension called QuickMD, which you may find interesting. And of course, one of the major issues in running those simulations is the accuracy of the force fields that you use as input. And he will also talk about such efforts. Now, if you think about the logistics, I'm not sure if you have already downloaded the software that will be used. So it will be the first 2 days, actually. These are the essential 3 software that you will need. The first 2 days, you will need to use Prodi. And then the last, but also Prodi uses VMD. So you need to have these either in your laptop or you use the computers that are available in our computer lab next room. So if you haven't done that during the lunch break, that might be a good time to make sure that you have all the software downloaded. And then we have a dinner on Thursday night. You're all invited. unless you have other plans. As you've seen, we serve breakfast. We will be serving breakfast and lunch every day. You don't have to have lunch or breakfast here, but you are more than welcome to do so. For lunch, in case you want to go and see new places, I recommend a few nice places all within walking distance. So we would like, and there'll be a photo on Thursday lunch break. We would like to make sure that we've done that in previous years. So that was, I don't know, from probably 2 years ago with Klaus Schulten and Zaida Schulten. And another one, again, from past year. So that completes, I think, my brief welcome talks. Of course, the goal is there is a microphone now. You can hear better, perhaps. The goal is to learn here as much as possible. All the lectures are made available on the web. And we'll give you copies of, if you are interested, I don't know if you would like to carry them, but we can also provide hard copies of the lectures. So we will make everything accessible here. So it's up to you, how much you would like to take notes. There were, I think on the web there were lectures from last year, which we have updated. So we will provide the new updated versions. Now, as I mentioned, we are running this new center, Biomedical Technology and Research Center, also called a resource, called MMBioS. And we make accessible a number of servers. One of them is the A&M server, and you will see, we will talk about that. The A&M stands for anisotropic network model. We also make accessible a database, IGNM database, Gaussian network model database. So let's see. Which permits us to make accessible the results that have been evaluated. In case you are dealing with a large structure that may take time, it might be a convenient resource to use to learn about some results. We will talk about all these things. And PRODI is the major API. API is Application Programming Interface, which will be described here. And also the most recent interface which has been developed with the leadership of Hongchan is Dynamics. As you can see, this has been, actually this needs to be corrected. It has been published in 2017, right? Not 16, Dynamics. Yeah, it just appeared newly. So that is like a resource that integrates many, many others that we have developed. I would say that you can get away with using Dynamics and PRODI alone. A&M is very easy to use. You may like it. IGNM has the advantage of retrieving the data already pre-computed. But E&M already has all those features. Dynamics or E&M stands for Elastic Network Model, already contains all the features. And this has been designed for biologists, for users who are not very comfortable with programming. And it is, to our view, it has been designed in a very user-friendly way to make it easier for you to, in an intuitive way, to find answers to your questions. So no need for programming. It is interactively, you can retrieve lots of information on your query, protein or structure complex assembly. PRODI is slightly different. You need a Python language, Python, at least some minimal knowledge of it. However, the tutorials, everything is so instructive that you can easily learn and apply them, as you will see. So it is more for, this is from computational biologists, I would say physicists or chemists or engineers or computer scientists. And this is for a broader community, I would say, including biologists, experimentalists. All right. So, and I would like to acknowledge that Ahmed was the main developer of ProD, a former PhD student of mine, currently working at Google in Silicon Valley. And Anindita, again, another PhD student of mine, played a major role in the later stage development of the of ProD. And currently she is also working for a biotech in the West Coast. She has a senior position. I will remember the name of the company. But so these are the two major developers. But then I have also benefited from former postdocs who are now professors at the University of Pittsburgh, Tim Lezon and Chakra Chenupotla. We have published several papers together. And another former PhD student, also currently employed at Google, is Ying Liu, who has been in charge of extending ProD to also take advantage of sequence data, not only structural information. And currently, Jihan and John are, I think, the two students in my lab who are really in charge. Especially Jihan has been, contributing a lot to further development. So the original, the two references which you will really need to see would be those two papers. Again, I can make several copies of those papers available for those of you who would like to take. Or you can easily, of course, read from the web. The original paper was published in 2011. And then the extension to bridge between sequence evolution and structural dynamics was published in 2014. And we anticipate now publishing a new version in 2017. Because since then, there have been really lots of advances. So that gives you a summary of where, let me see if I have a pointer. Yeah. Unfortunately, this doesn't. So this gives you a summary of the statistical data so far. So we have probably what you may consider is Google Analytics stop taking data for the number of downloads, but we have the number of in last year. But we certainly have been more than 500,000 downloads since its inception in 2011, which is quite new. It's relatively new in the field. And this is about the total number of visitors, among them the unique visitors, about 70,000, and from 136 different countries. So this shows you, actually, this gives you an idea of the broad usage of ProD. We are extremely satisfied with this. And a little bit more about some statistics. We have here, if we focus on what Google Analytics is showing in the last year, we had 16,000 unique users. This is how the usage profile has been in 1 year. Why is it periodic like that? So there are more users and then less, more and less. What is that? Can you guess? No, actually, we are talking about a year here. So the period is much more. The frequency is higher. Weekends, exactly. So people don't work at weekends. We can see that. And there's a period of time people don't work either, around Christmas. And I don't know what happened on that particular week. But so that's it. I think that's very interesting. It shows very clearly that we really work in a periodic way. So this shows the distribution. And during Christmas, everybody is taking some time off, apparently. And then so who is using it? I thought also, again, from the last 1 year, statistics, everything is online accessible. You can see all these things. It was interesting to see who are the top 10 countries users. Of course, United States is the first. Number of users, as I mentioned, it was the last year, 16K was unique, and 31,000 is the number of users. United States is number 1 by far. And then India and China and UK and Germany and Brazil. I was very interested in that. France, Japan, Canada, Italy. And then comes Spain. The 11 was Spain, actually. So that is a little bit showing how broadly we are. We receive, queries from different places, users from different places. Now today, in the afternoon, you will be given the basics for using Prodi together with its visualization interface, NMBioS. NMBioS stands for Normal Mode Wizard, okay? And Prodi, what is Prodi for? Prodi dynamics, obviously. So we could have called Prodi, but for some reason it became Prodi. And then tomorrow we will talk about other extensions like Evolve, about evolution, how we can take advantage of sequence information as well to increase, to do more. And then how we use that interface to do druggability simulations. That's another application we'll talk about tomorrow. Okay. Now, those of you may already have seen that. In case you haven't, if you go to the Prodi website, if you type in Google Prodi and let's say Bahar, you will see immediately. On the Prodi website, here, there is a new menu, workshops. If you click there, then you will have information on the current workshop. You will have access to the lectures, to all the Python notebook that will be used. So you will, you can, I think it is the most convenient thing to have everything accessible on the web, but you can always, it's possible for you to print things. All right, so let me give you a little bit more background. So how many of you is going to use his or her own laptop? Almost everybody. So that's a good thing, and you can, this way you will be able to download everything and then be able to test everything. All right, so let's talk about the main idea behind the development of Prodi. Everything we do is based on what's called network models. Network models are everywhere, of course, in biology, in engineering, in many different disciplines. Here we apply them to biomolecular structures dynamics. The advantage of network models is that we can apply them to large systems. We can also incorporate structural data at multiple levels. And the way we started, actually, my PhD topic originally was polymer physics. Is there anybody doing with polymer science background here? Kind of. And also chemical engineering. Any engineering background? Okay, good. Chemical engineering is a good starting point. So that's the way I started originally. So I've taken really advantage of principles and theory and methods of polymer physics in addition to computer science methods like or graph theory, spectral graph methods, as you will see. So one key concept is that structural information is great. We are really very pleased to have structural data in what's called the Protein Data Bank. Are you all familiar with the Protein Data Bank? PDB. But that's, to us, that's only the starting point. That's our input. We use the structures from the PDB, and we animate them. You know, we can see, we try to see what they do, how they move. So for example, in this case, we're talking about a molecular machine, in a sense. This is a bacterial chaperonin, which is supposed to facilitate the folding of unfolded or misfolded proteins. It's a huge structure. And then using our current tools, it is possible to observe how, under equilibrium conditions, this structure undergoes fluctuations. Okay? And we can see how, for example, the neighborhood of those two rings here changes during those fluctuations. And you will see why these things are important later in the lecture. Or we can focus on the global motions. So here there is a cap, if you like, co-chaperonin, the structure of which changes coupled to the other two portions of the molecule. So we are interested in using we are interested in what we call the global motions. Global in the sense that they involve the entire structure. They are not localized. So, okay? So we have two types of motions, broadly speaking, local or global. And global motions, they are important because they are really what the overall structure favors. And because the overall structure favors this type of intrinsic dynamics, we call it intrinsic dynamics, it is what the structure is going to do during its biological activities. These are these type of motions that are being recruited for biological functioning. So we learn about biological function based on mostly global motions. All right, so here are some examples. For example, this was, again, a former PhD student who analyzed a viral capsid together with the DNA inside, the genetic material inside, satellite tobacco mosaic virus. And we can see now how the structure can breathe, if you like, can change, or how the different structural changes take place in different subunits. An example, and James is going to talk about that example during his afternoon session, is AMPA receptor. I've heard that many of you are interested in transmembrane proteins. AMPA receptor is one of them, which plays a very important role in synaptic transmission, regulation of neurotransmission. This is the transmembrane region, so this is all the extracellular region from here up. Yes?
Are you showing us projection pathways between two known structures, or are you showing calculations?
These are calculations. Very good question. So many people, when you have two endpoints, they extrapolate some kind of morphing. In our case, we take the PDB structure itself, and then for a single structure, we try to see what are the most accessible rearrangements. So there is a spectrum of different modes, and we focus on the most collective modes, which we call the global motions. So this is, in this case, I don't remember, James, is it the first or second? This was the second most collective mode of motion. And we were very interested in this one because it gave us one way of testing whether this type of motions exist. This is from a paper that was published actually a year and a half ago. So it tells us, so what we've done is the following, just to give you an idea whether these things, these type of motions that are being predicted by PRODI are meaningful or not, we considered a pair of residues at this position in the crystal structure. They are separated by about more than 30 angstrom if you take the crystal structure as is. Okay? So two residues. Now, according to our computations, they come into close proximity. You see this type of motions. And we have written here the distance, you know, as it changes from, let's say, 710 up to 50. Okay? It moves all the time, the distance. Now, we said if these motions are real, we can test them experimentally. How? You substitute at those positions cysteines. What do cysteines do? They form disulfide bridges. Now, in the presence of an agent that will facilitate the reaction. And then that's what actually Ingo Gregor and James Krieger, who came from Cambridge, University of Cambridge, United Kingdom, MRC. That's what they've done. Actually, they have substituted cysteines there and observed that indeed there is a cross-link formation between those two sites, which otherwise, under static conditions, would not come into close proximity. And more than that, this motion is also important for functionality, because then the biological function, signaling function of AMPA receptor was also impaired. So that is the, we start to learn about some mechanisms of motions that are also functionally relevant. And we can also come up with some hypotheses that are testable. Okay. Still about the general philosophy. Now, in the, I don't know if you can see that, but here are simulations at multiple scales. MMBioS is about multiscale modeling, right? So we use lots of analytical methods and also simulations, a combination of both. And at the molecular level, subcellular, molecular, as I mentioned, based on the elastic network model or other tools. Subcellular would be MCEL, the Monte Carlo simulation software for cellular events, subcellular events. Or we can do things at the cellular level, tissue level, using other tools like Cell Organizer. Now, our goal here is to bridge between those two scales. What happened in the literature is that, although it's all computational biology, people working at those different scales are completely, you know, unaware of each other's work. They just focus on a given scale. We would like to take advantage of what we learn at the molecular level to use in subcellular simulations, or map, you know, molecular events all the way to the organ functions, if possible. So that's the goal. So again, as I mentioned, we have those two representative scales. And so what we're doing, you know, I'm focusing on those two scales, but now we are expanding them to have intermediate levels. So for example, between molecular simulations and the cellular, subcellular simulations, we have new levels. One of them is the coarse-grained approaches based on elastic network models, which is the focus of those next 2 days. And then, of course, MD, but now there are accelerated MD, quick MD, which you're going to learn about, which are much more efficient than full atomic detailed MD. So the goal is to fill the gap in between, okay? So that's another, you know, way of putting things. Actually, these are different time scales versus different length scales. And at this end, we have QMMM, quantum chemical, molecular mechanics, hybrid models, and there was at least one person I heard. And your name was Joe. Joe and Dave are from Penn State. I'm trying to memorize. So you have this type of level. Then you have side chain motions, you know, jumping from one isomeric state to another, or loop motions, domains, etc. and all the way to cooperative machinery. Well, we are mostly interested in these multimeric structures composed of multiple subunits. In many cases, also embedded in an environment. We would like to model not only the system, but the environment in the context of all its interactions, cellular interactions. Okay, that's the goal. So, you know, this has been always my, the way I see it. From structure, we can learn a lot about function if we go through dynamics. So dynamics is the natural bridge between structure and function. All right, now I start. So these are the different items I'm going to talk about today. You will have lots of applications, but I think it is useful for you to know what the underlying theory is. So I will try to make it very, hopefully, comprehensible, the underlying theory. We'll talk about Alice theory, which is a very important phenomenon in structural dynamics. Ensemble analysis, how we can compare experiments, predictions, and then there are extensions. We won't talk about that today. It will be more tomorrow. So we start with the theory. When we talk about elastic network models, you may have already noticed that I talk about two different basic models, the Gaussian network model and the anisotropic network model. Can you find out if there is a pointer here? Maybe we can ask the PSC folks. I don't know. So there are two models, Gaussian network model and anisotropic network model. And in both cases, what I put here is one of the most recent publications, which in this case, for example, this is the IGNM database. And then the original paper that introduced the theory. And same thing here. This is the server which is designed for anyone without any computing background to use easily. And that is the original paper where we introduced it. Of course, between them, there are tons of other publications, but I wanted to give you just the perspective. And as I mentioned, I'm using my polymer physics background in a sense. And this, oh, thank you so much. You have one?
Yes,
this is yours? Okay, perfect. Thank you so much. So so Paul Flory was, he received the Nobel Prize in chemistry in 1974 as a polymer chemist. And he has been one of the, he has been one of the founders of polymer science. And he introduced elastic network models for polymer networks, actually, which we have extended and adapted to proteins. So what is an elastic network model? I'm sure you are all used to this type of ribbon diagram. By the way, keep asking me questions if you have any. So far, I'm sure everything was very easy, but you may start to. So we take a given ribbon diagram, and then we map it into a network representation, which I will explain how. And then here's a movie a former student generated, which might work. I don't know. By the way, that is a... OK, here is the... for an wow. Apparently, it's in the background. You can't see it. I'm sorry, you can't see it. So I'm afraid I won't be able to show the movie here because it is, well, I made the mistake of getting a new laptop this weekend. Yeah. something I should not have done. But I'll just continue with the. So the idea, it was just illustrating the way we take a PDB structure. And in the PDB structure, we focus on alpha carbons. We connect the alpha carbons which are within a certain distance range by those elastic links, springs, if you like. And then we perform, we analyze, we try to calculate what are the different types of modes of motions that are intrinsically favored by the structure. So here are a few examples. We'll not go into more details one by one. So this is Gaussian network model. Here is the network representation. So the network is composed of nodes and springs. Okay? And each node represents one residue. Where is it located? It's located at the alpha carbon position. So in the PDB, you have coordinates, x, y, z coordinates for the alpha carbon position. This is the original position vector of residue I. So we are talking about individual residues now, and the residues could be amino acids or nucleotides. It's applicable to both proteins and DNA, RNA. So these are the original positions. These are the fluctuations. Now you have elastic springs that connect them. The name Gaussian comes from the fact that we assume each node to be subject to, I can use that, Jian. And I can give this back.
This is laser.
Which one?
Laser.
Okay. All right, thank you. So we have, thank you very much. So we have Gaussian fluctuations, and the interresidue distances, the distance Rij is the vector, the Rij is the vector that connects node I and J. Changes in this vector, and I think it is shown, changes in this vector will be, this difference will be expressed as a difference in the fluctuation of the individual nodes. So this is simple vector algebra you might be familiar with, okay? So that is the notation, at least, that we're using. And the idea is to represent the overall fluctuation. Fluctuation is the displacement from equilibrium position from the coordinates listed in the PDB. Are you with me? The instantaneous fluctuation we can write as a vector for the first node, second, for a protein of n residues as a vector. So here is probably a more detailed view. You have the position of the first ith node and jth node. These are the corresponding position vectors. This is the vector, distance vector between the two. And during the motions, this will be displaced to that position. This one is displayed to that position. These are the corresponding respective fluctuations. And this is the final distance. And the change in the final distance, the difference between the two distances, is given as the difference between their fluctuations. Very simple, straightforward. Okay? Is it? Okay. Now, that is important. Here we wrote the same thing. This is the fluctuation of individual amino acid at a given point time, tk, let's say, kth time point. You will have its instantaneous position with respect to its original position. That's the fluctuation. Okay? Now, under equilibrium position conditions, which means you have a given structure, it's moving around that structure while it is maintaining. Proteins function under equilibrium conditions, okay, under physiological conditions. So all the motions we are trying to describe here are the motions that are accessible to the native structure. We're not talking about folding or unfolding. We're talking about what we call equilibrium dynamics or structural dynamics. Okay? So how the protein just dances, moves around its equilibrium position. That's all what we are talking about. Now, under such equilibrium conditions, the fluctuation, if you average over all times the vector, it will be equal to zero, because there is no reason for the proteins to start from one conformation and land somewhere else, right? It's just moving around it. It moves like that, like that. So this is a vectorial sum. Vectorial sum of all random motions is just zero. But what is not zero is the size of the motion. If you take that quantity, the vector at a given time, square it up, now you have a magnitude. You move a little bit here in this direction and a little bit like that. So the square of quantity, averaged over all time snapshots, is not zero. This is the mean square fluctuation. The mean square fluctuation is a very, very important quantity. We would like to analyze what's the mean square fluctuation of different residues. Why? Because if we know the mean square fluctuation, it gives us information on the relative flexibility and adaptability of those residues, for example. Regions that, okay, let me ask you questions, let's see if you can have some answers. Suppose a given residue doesn't fluctuate much. Its mean square fluctuation is very small. Do you expect this residue to accommodate mutations? It's very tightly packed now. You won't. And indeed, regions that show small mean square fluctuations are evolutionarily conserved. Okay? On the contrary, if you have a residue that moves a lot, shows large mean square fluctuations. Now, because of this high flexibility, you would expect this to easily, accommodate mutations or bind substrates in an optimal way, because it can rearrange itself to maximize in a favorable way or minimize energetically its interaction with the substrate. So that because of that, usually, the residues that show peaks in the mean square fluctuations, we try to see they would be usually on the surface of the protein. Those that show very high mean square fluctuations are likely to interact with other substrates involved in recognition, at least. Even when they bind something, there is an entropy loss, which is not good. But the energy of interaction is so favorable that it usually more than compensates the entropy loss. On the contrary, the minima in those mean square fluctuation profiles will show you those regions that are very highly constrained. We'll come to that, okay? Now, what was the inspiration based on the polymer theory? Well, apparently, actually, there is a model introduced by Rouse. Rouse wrote this one paper. I'm so impressed by him in 1956, and that's all. And he became very famous. It takes only one good paper sometime to be cited 50, 60, 70 years later. So what Rouse said, he introduced this classical bead and spring model for polymers. Polymers, the major difference, these are also macromolecules like proteins. The major difference is that they are more expanded, right? So everything is just connected to its first neighbor. There is no connection between the second and the nth residue, for example, because they are more expanded, not contracted. So we have the same equation that I mentioned. Now, it is valid only for all connected pairs. The distance applies to only connected ones here. Well, you can write something for all pairs, but here we are. If you want to write the total energy of a system of harmonic oscillators here, beads and springs, you can write as a sum like that based on all pairs. Or you can replace it by that, delta R1 to be replaced by the difference in fluctuations. And then we use the same force constant for all springs, uniform force constants. Well, this type of expression for the overall potential can be expressed in terms of what's called a Kirchhoff matrix. Kirchhoff matrix is a matrix that gives you a description of the network, if it's a network connectivity. Now we have a network here, except that it is just all the connections are between the nearest neighbors, okay? So in the Kirchhoff matrix, the off-diagonal terms, here -1, -1, -1, are the negative. All the off-diagonal terms are -1 or 0. They are -1, the rest is 0, not shown. They are -1 if those two bits are connected. This is the definition. Now, the 1, 3 element is 0 here because 1 and 3 are not connected by a spring, okay? So then we have something like a band. 1 and 2 is connected, 2 and 1 is connected, 2 and 3 is connected, 3 and 2 is connected, etc. And then the diagonal term by definition is the negative sum of off-diagonal terms. So here it was -1, 0, 0, 0, 0, 0, so the diagonal is 1. Here it's -1 and -1, and the rest is 0. The diagonal is 2, okay? So what is the physical meaning of the diagonal term? 1, 2, 2, all the way 2, and then 1. What is it? Who said so? Yeah, yeah, exactly. So this gives us a measure of the coordination number, if you like, how connected. So these have two neighbors, everything, except for the two terminal residues, which have one neighbor, okay? One link. So that is indeed, that's also called connectivity matrix. And in computer science, in graph theory, the number of springs here, the number of connections, is called the degree of that node. So that one has degree 1, and the rest have all degree 2. Okay? Okay, that's a definition. By definition, when we build the Kirchhoff matrix, and everything will be defined by the Kirchhoff matrix, we need to understand that. By definition, we want a matrix n by n for a macromolecule of n beats, n by n matrix, and we start with the off-diagonal terms. If two beats, let's say beat 3 and n, they are not connected, right? If they are not connected, I say 0. There is 0 connectivity. If they are connected, let's say 3 and 4 here, if they are connected, then it's, I call it -1. There's a minus sign. So it is actually either ones or zeros, like a binary system. But by definition, we use -1 because then the product is going to be, when you calculate the energy, it's going to be positive. So -1 whenever two beats are connected, 0 if they are not connected in the network. And the way we construct, again, the Kirchhoff matrix is all the diagonal terms are the negative sum of off-diagonal terms in the same row or in the same column. It's symmetric, right? Is this okay now? Okay. So the thing is that when you have this Kirchhoff matrix, if you pre and post multiply it by these fluctuation vectors, if you do the operation and you add also this force constant, well, the product turns out to be the overall total energy, which is used in the Gaussian network. So the Gaussian network has a certain energy potential of mean force, if you like, which is accounted for by this product. And this is a concise representation of this operation. Now, in a sense, the way the Kirchhoff matrix looks is something like that. The diagonal elements are populated because they are spatially close. And then in the proteins, instead of all zeros here, we have also contacts between farther neighbors. So we have a series of -1s here, over here. You see what I mean? So it's pretty much like a contact map, if you are familiar with. And so these are, this band will be referring to things that are sequentially close. Now, if you have a band like that, for those of you who are familiar with contact maps, what would this one indicate? You know, you have residue I and j interacting, connected. I plus 1 and j plus 1, I plus 2 and j plus 2, I plus 3 and j plus 3. They are all interacting with each other. These are beta, yeah, 2 beta strands. And because the numbers are increasing in the same way, they are parallel. Okay? Or if it's anti-parallel, it would be like that. Okay? Or something very close to the diagonal will be the helix. So we even by looking at the contact map, we know some secondary structural properties, right? All right. Now, so this is the definition of the Kirchhoff matrix, which I just explained. And the diagonal is sum from the negative sum of diagonal terms. Now, there's a whole statistical mechanical theory behind that. And I'm not going to go into that. But whenever you want to calculate an average quantity in statistical mechanics, you take the quantity, you multiply it by its probability, and all the values that it can assume, each of them weighted by its probability, the Boltzmann factor, and integrate over all of them and normalize with respect to the, let's say, partition function. This is the general rule, right? But if you do this type of integration, you can take this integral. This is called a generalized Gaussian integral, actually, where you put the expression for the potential. But we're not going to go into that. I will give you the solution. The solution is as simple as that. So this quantity is the fluctuation of residue I and fluctuation of residue j, and their dot product. So this is called the cross correlation between the fluctuations of. So this residue moves like that, this one moves like that. And what is the cross correlation? It depends on the magnitude of the motions plus the angle, you know, the direction. That product is of two vectors uv, you know, magnitude of u, magnitude of v, times cosine of the angle in between. So that is the cross correlation. Now this is you know, the Boltzmann factor, absolute temperature, they come from this Boltzmann constant, they come from this Boltzmann factor. But you can forget that as a proportionality constant. It is what we are saying here is that the cross correlation between the motions of residue I and j are given by the inverse of the Kirchhoff matrix, ijth element. That's as simple as that. Now you have the Kirchhoff matrix, you invert it, you look at its ijth element. This ijth element is the cross correlation between I and j. So if you would like to calculate the cross correlation, what you do is you build the Kirchhoff matrix, you invert it by a root. Actually, this is called a pseudo-inverse because of the properties of that matrix. But you can calculate it very easily using a, you know. And then the ijth element will be the cross correlation. Or alternatively, the ith element, the diagonal element of this inverse will be the mean square fluctuation we're familiar with, right? And the ijth element is the cross correlation. So these are two most important quantities that we calculate. I already spoke about the significance of mean square fluctuation. That is also equally important. You know the term allostery, right? When two things are coupled. Now, if two residues show a very strong cross correlation, it means whenever you move one of them, the other needs to move at the same time. Usually, things that are close in space move together, but sometimes you can have even effects between residues that are far apart in the structure. So these are the allosteric effects. You bind something to this residue, it just rearranges itself. But this rearrangement is accompanied by a motion here because of the intrinsic dynamics of the protein. So cross correlations are very important. Are you with me? Yeah. Now all that, does it make sense? We need to compare with experimental data a little bit. So suppose we compare with originally when we did that, we compared with the B factors. What are the B factors? In the PDB, are you familiar with B factors? Who knows what B factors is? Okay. Exactly. In the PDB files for each atom, you have the XYZ coordinates, but then you have another column. So in X-ray crystallography, when they resolve the mean position, XYZ position, they also report like an error, how much this position is, seen in X-ray by X-ray crystallography. It's like a measure of its mobility in sense, because it's going to be broader if this position is not well defined. So B factors is a measure. B factor is a measure, also called Debye-Waller factor, is a measure deviation from the mean position, or the mean square fluctuation in a sense. And that's the relationship, actually. B factor for atom I will be scale. So forget this proportionality constant. We're always interested in qualitative features. The proportionality constant doesn't matter to us, but we would like to see, we know that the B factor for atom I, will be directly scaling with the mean square fluctuation. Theoretically, we know this theory. Now we can check whether our elastic network model gives something reasonable. We can calculate that, right? We can build our Kirchhoff matrix, invert it, look at the diagonal element, ith element, and then compare to the value that's reported in the PDB already. Okay? So when we do this type of comparison, we can see actually how well the theory gives a description of the mobility of individual residues. I have to say that the X-ray crystallographic structures, the B factors have other effects, but at least we want to see if we are in this right ballpark. So this is an output from dynamics. Remember, that was the latest version which integrates everything. So I was playing last night, and I took by randomly a structure, totally randomly, which turns out to be a crystal structure of 2 viral peptides in a complex with the MHC class protein. So now, when you go to dynamics, and Honchan is going to show you such very simple things, and you just need to enter the PDB code, if you know it, and of your favorite system. And it's going to give you a series of output files, among which you will see also the theoretical B factors. I'm sorry, the experimental B factors versus the theoretical B factors in a ribbon diagram. Theoretical B factors are nothing else than our mean square fluctuations, rescaled, okay? And now this is a color-coded diagram with the red regions showing the most flexible regions moving a lot, and the blue regions being the less flexible. So you will be able to play with these things. You will see it's very easy to do that. But then on the same page, when you scroll down, you will see also the corresponding curves. In this case, we're talking about a structure, PDB structure, that has 3 chains. Remember, there were those 2 viral peptides plus the MHC. So you have, as a function of residue index, you have the B factors. And you have we call them theoretical and experimental. Theory is our mean square fluctuation. Experimental is the B factor reported. And you have the curves. For example, for chain A, you have this light blue curve, okay? But that the theory predicts. And you have the black curve here is the same thing that experimentally they reported. So you can see how theory and experiments compare. For each individual chain, you can play with that, you will see. But the idea is that we can obtain a correlation between theory and experiments of the order of 0.6, 0.7, usually. Think about it. The theory is so simple. Nothing nothing other than the connectivity. And you obtain a very sophisticated curve, actually. This is nothing else than the diagonal elements of the inverse of the Kirchhoff matrix, remember. we plot as a function of residue index, and we compare with experiments, and we already achieved a reasonable level of correlation, which gives us confidence about, I mentioned that the B factors are affected by many effects, and one of them is crystal contacts. I don't know if you've seen this type of images. This is how a crystal looks like. Now, this is the protein, but the protein in the crystal lattice environment is surrounded by many other proteins. This is not the way it is in our body, right? Normally, it's in solution. So all these neighbors, they are reporting now the B factors for, let's say, one protein. But that protein is making what we call crystal contacts with its neighbors. Because of that, actually, this region, this loop here, is not going to move as much as it would be moving otherwise in solution. So the B factors have this type of artifacts that come from the crystal environment, of course. And even for the same protein, it's very interesting. You can have different types of lattice arrangements, and then you would see that even for the same protein crystallized under different conditions, the B factor curves may show some differences just because of those crystal contacts. So this is the region I show, that there are those contacts, and we would expect those residues. What would you expect the mean square fluctuation of those residues to be compared to theoretical predictions? Less. They will have lower fluctuations, right? And so actually that's what happens. Of course, your intuition is correct. So we have the results now here, several curves. Now the theory predicts this green curve, okay, for the mean square fluctuations. What the PDB file gives us is, I don't know, it could be the blue or red, one of them. Okay, let's say the red curve is what the PDB factors are. And there is a huge difference here at those points. Why? Because those points refer to these regions that make those crystal contacts, and the mean square fluctuation is much lower compared to what the theory predicts, the way you expect. Then we play the game. The theory is so easy. You could construct the entire structure, not only for your protein of interest, but everything surrounding it with the crystal lattice neighbors. And then we re-evaluated what the B factors of this central protein would be. Now we are taking not only this one, but we take all this structure, and we are re-evaluating what the B factors are going to be here, right? And then when we do that, then we obtain the other curve. You can see here, the red curve or blue curve, which exactly coincides with the experimental data, showing that we can predict exactly the same profile. We can make the theory as wrong as the experiments, if you like, and have good agreement. But the reality is that there's much higher fluctuation at those points. Yes?
Sorry, what you did in this case was you allowed the other contacts?
Yeah, we built a bigger network. So in our network now we have multiple proteins, and they are actually forming a network because some of the residues belonging to different proteins are very close. Now when we did, we have now this huge, bigger Kirchhoff matrix which we invert, and now we are looking at the central protein in the presence of its neighbors. The neighbors, we call it the system, and the environment, and the central protein is the system. So we have this method system and environment in our interface. When we look at the system in the presence of the environment, now the predictions exactly agree with experimental observations, because that's the way experiments are recorded. Okay. So an application to a protein, something published in 2003, hemoglobin, you're all familiar with, is a tetramer. And here is again the comparison. Now you are familiar with this type of plots, residue number versus B factor theory and experiments. So you will be able to evaluate this type of mean square fluctuations very easily. You can do this with simulations as well. Simulations may take weeks if not months. This is within less than a second, you obtain this instantly, this type of data. The calculations are very fast. Now, what is this? This is the cross correlation, which I mentioned. Now, we have the residue indices, which and we look at the cross correlations. Now, if you look at this cross correlation map, remember the diagonal elements are again like the mean square fluctuations here, and off-diagonal terms are the cross correlations between the motions of residue pairs. What do you see? Because it has 4 subunits, alpha 1, beta 1, alpha 2, beta 2, I just labeled them. If you look at this cross correlation, one part of course, half of the job is to generate data, the other half is to interpret it, right? Which is even more important and more challenging. So when you look at that, what do you see here? Without knowing anything. It is symmetric, for sure. If I is correlated with, if I moves together with J, J moves together with I. One more thing, I see a block here and then a block there. And then very weak signals elsewhere. What it tells me that the alpha 1 and beta 1 are kind of coupled, and alpha 2 and beta 2 are coupled, and there are weaker correlations across those pairs of subunits. Actually, this tetramer has been called a dimer of a dimer. It's as if, there is a very integrated dimer and another integrated dimer. And then we can see immediately, if you were looking at this structure, could you tell me which particular subunits are more coupled? But when we do the cross correlations, this really is clearly seen, which monomers, which subunits are more coupled. So that is this type of information that you can learn about coupling. Is it being recorded? Okay, then I need to put it back. Okay, let me show you a few examples. Now, we started to talk about cross correlations, right? The cross correlations, as I mentioned, they provide information on the relative movements of pairs of residues. In many cases, you will see that in the software package, the cross correlations will be normalized with respect to the mean square fluctuations. So what we're doing here, you remember, this product is the magnitude of residue I motions, magnitude of residue J motions, plus the orientational correlation, cosine correlation in between. Now, by dividing by this, I get rid of the magnitude of the motion, and I fully focus on the orientational correlation. So whether they are moving together in the same direction, in an opposite direction. So that is, for example, here, this normalized cross correlation varies between -1 and +1. This is like a cosine. So if it is +1, it means the two residues are moving like that. Okay. If it is -1, how do they move? A little bit of exercise. You need 2 hands. You can't show. Exactly. So I didn't see hands there in the back. How do they move if they are anti-correlated? Okay, you make I tend to do that. But that's equally correct, okay? I tend to do that, yeah, when I show it. So they move same, it's the same direction in a sense, but opposite senses in vectorial terminology. Okay? But in reality, this orientation correlation is anywhere in between. What is 0? They are can you show that? They should move at the same time. Perpendicular, one is moving like that, the other is moving like that. Can you do that? You can't, our brain is so, but the protein does. One is perpendicular, yeah, okay. So this is uncorrelated. 0 is uncorrelated. Sometimes it may be correlated, but they are really perpendicular to each other. And you can have a whole spectrum, some of them moving together in opposite. Now we know how the relative movements take place. Now again, in this either IGNM database that I mentioned, or suppose you enter a code protein name, you can look at the output. These are the cross correlations. So this series G index from, this is a small protein in this case, from 1 to 120. Remember, I used the color red for correlated, and blue for anti-correlated. Anti-correlated is also correlated, actually. It's a strong correlation, but moving the opposite direction. So here, you would expect to see a red region here. Why? Because after all, they are connected, right? They push each other. They move in the same direction, more or less, okay? Connected residues. But then you have a larger region. That's a region, for example, this part moves as a block. They all move together. Or this part means that this block and that block move in opposite directions, okay? Now you can even think of some domains, substructures by just, for example, I can see here a square. What does it mean? That particular region from 60 to 100 is really moving very coherently as a block, almost as a rigid block, in the same way. But that same region is anti-correlated with respect to the remaining part of the chain, the tail. Are you with me? Do you know how to understand those maps now? Yes.
How do you explain not fully correlated versus not correlated from the map? Like -1 and 0 from the map.
-1 is correlated. It's anti-correlated. It's
versus
blue. Blue. Not correlated is white. The regions that not correlated are the regions that apparently undergo perpendicular movements. Was this your question? Okay. Sure.
If they move in perpendicular, they're correlated in the perpendicular direction. Is that no correlation, or is that?
Well, this is the way we this is the way we interpret. We, you know, whenever the correlation cosine is 0, because it's an average over several different movements. Normally, we are summing over all possible modes of motions. I'm coming to that. So if they turn out to be, the average turns out to be 0, the correlation cosine, it means that they can move anywhere. So it's not like a single motion, single mode, where they are perpendicular, but actually what we are observing here, as shown by the angular brackets, is an average over several different motions. So it means that when this one is moving like that, the other one can do anything. So that's why we call it, the average is 0. Okay. Thank you. That's a very good point.
So typically if you consider protein, would you say that something like a free loop has 0 correlation?
Yeah. Usually you may have, a loop region may be uncorrelated with respect to others. But if it is a loop involved in some allosteric action, whenever it moves, there may be another region that is coupled, you know, allosteric recognition of a substrate, right? Okay, very good. I have questions. Yeah, the blue regions move, you know, you've shown like that. What happens in this protein, it's very likely that we have two domains which undergo like a cleft opening closing motion. Okay. So the blue regions will be this block versus that block moving in opposite direction with respect to each other. Then there is a hinge site in between, right? Between the two clefts. The hinge site is not going to be correlated, so it will appear like a white region. So the passage from this red to blue will be actually the hinge site, because this is moving coherently. That part, if you were looking here, is also moving coherently, but they are moving in opposite direction with respect to each other. So this is one part, this is the other part in opposite direction. And in between, you have no motion. It's like an anchor in between. So this is a hinge site. We call it a hinge site, which doesn't move in space. Is this what you ask? I don't know.
Yeah, I guess if you can be more, I guess, motions of the wings, not the, yeah.
Okay. And James.
If we decompose into lift, then we can, as the error correlation, then we can maybe say that things are predicted because they got the error and they're going to do it in the same direction.
If we decompose into modes, that's the next thing. We're going to do that. So this is this. Actually, even here, I have put together 5 first modes. You know, you can select the number of modes that you would like to include, but I haven't yet explained. That's the next thing we're going to cut. Okay, we'll get there. So again, you can do from dynamics also the same thing. This is the previous protein. You remember we had 2 viral peptides. Now I can see there is a block here. There is another block here. It gives you some information on domain separations, if you like. And then there is another block here. Actually, in this case, these 2 blocks belong to the same peptide, viral peptide. This is the second chain. It's that. And then there is a very small third chain there. So you can see some domain or subunit separations. All right. And now I mentioned here. Here in this case, we took all the modes from 1 to 380. So this is the resultant of everything. The reason you see 2 plots like that is, you will see, Hong-Chan will explain. If you can select regions here, which you can enlarge there, and you will have lots of data. You will see. Now, one thing I wanted to mention is this cross correlations. You know, we have a map, like, or the elements of the map can be expressed as the elements of a covariance matrix. Cross correlations define the covariance matrix, and remember this: the covariance matrix we just obtained by inverting the Kirchhoff matrix in the very beginning, right? So there is a fundamental relationship. The connectivity inverse of it gives you the covariance. Intuitively, it also makes sense if, at least think of the diagonal terms. For the diagonal terms, if the connectivity is very high along the diagonal terms, if something has many, many neighbors, its inverse is going to be small, right? The mean square fluctuation is going to be small. So you understand physically what we are talking about. Higher connectivity means lower mean square fluctuations. Things get more complicated in the cross correlations, but at least you understand the logic. So this is the way the covariance matrix looks like. You have the covariance between all pairs of residues in an n by n matrix. So these are the elements that we have mentioned. And as James pointed out, actually we can decompose. Now these are so far what we've seen is observables, which we can compare with experimental data. But to us, even more interesting is to find out what is hidden. What is the underlying propensity? And this is done by decomposing, let's say, the covariance or the entire motion into the contributions of individual modes of motions. We have what we call a mode spectrum. Okay? And the mode spectrum, you know, maybe you've seen in high school, if you have a string, one mode is the one that involves the entire string, right? The next mode will have a smaller wavelength, and then the third, etc. So you go from the global motion of the string to higher motions as you have smaller frequencies, smaller amplitudes, if you like. So we can also find do this type of normal mode decomposition. Normal means, in this sense, the modes are perpendicular to each other. So this is like a set of variables that form a complete space, orthogonal to each other. Well, So we can write any cross correlation as the sum over several modes contributions, okay? So we have K is the mode index, you have several modes contributing to this cross correlation. And remember, this was found from the inverse. So the contribution of mode K is simply, there's a simple, well, there's a matrix algebra here where you take the Kirchhoff matrix, you decompose it into a contribution of different modes by what's called an eigenvalue decomposition. Again, you don't need to do it manually. The program will do it for you, but what it is doing is it is decomposing this covariance matrix now into a product of eigenvectors, here UK, and eigenvalues. So we can write separately, what are they? The eigenvalue, the eigenvalue gives you the inverse eigenvalue gives you like a weight for the occurrence of a given mode. So if it is smaller, it means that it makes a bigger contribution, right, to the sum here. If it is smaller, it means also that we are talking about a low frequency motion, what we call also a soft motion. And the eigenvector is describes how the protein changes in that mode. So conceptually, I don't want to go into more details, but the bottom line is that you can write any cross correlation or mean square fluctuation as the summation over several modes, which you can easily identify by eigenvalue decomposition. Now here, are you tired? Do you want a break? Maybe yes, but let me finish that part and then we'll do. So the slowest global mode, that's the shape it looks usually. And if you go to the other end of the spectrum, now we're talking about very localized, not motions, and then we'll see peaks here. So these are high frequency modes. These are individual single residues that are under high energy, high frequency, high energy, okay? And those peaks that we observe at this end of the spectrum, the fastest modes, are, as I said, they have very high energy, high frequency, and they would not normally sustain any substitutions, mutations. They are usually very conserved, evolutionarily conserved. In the other end of the spectrum, and we are more interested in the other end, the global modes, the shape is going to give you information on different functional regions. This was for HIV protease, by the way. You will see that usually the active site of enzymes, I heard some of you were interested in enzymes, the active site won't move at all in the global mode. You don't want it to move. Why? It's, the active site has those catalytic residues that are positioned in a very precise way to function. That should be maintained. But around the active site, there are those regions that move a lot, including this peak here. Remember, I said the peaks would be recognition loops. So that is a recognition loop. So by looking at the slow mode shape, of course, and also having the structure in front of you, you can start to understand why certain regions are moving more, why others are minima. Here it's a hinge site with respect to the two parts of the molecule. So that is what we analyze. And you will have, essentially the idea is, when we look at the slow modes, remember we are talking about an equilibrium structure, right? That was the beginning of the lecture. So we are sitting at this energy minimum. This is the energy landscape. We're sitting here. And this is a multidimensional energy landscape. So we have multiple dimensions which we cannot show. This is the energy height, and then we have multiple dimensions. I'm showing only two of the dimensions. Okay? Our system cannot visualize more than that. But the softest mode here, the global mode, is by definition the direction of motion that would be involving the largest movement for a certain energy rise. So suppose you feed your system, you perturb the system, you give it an energy of that amount. Now it's going to move in the direction which is, or it will be moving at a place where the major conformational change will be along the softest mode, okay? Although it also moves simultaneously in other directions, the largest movement will be along the global mode. Again, an output for the same protein, this system of two viral peptides and the MHC, major histocompatibility complex, a major part of our immune system, for those of you who are interested in the biology. Now, in this case, we have again in dynamics the color-coded diagrams. One of them here, this is for mode 1, this is for mode 2, and this region moves a lot in the mode 1, and in the mode 2, that region moves a lot. Here, these two regions, remember, this is moving a lot. This is almost fixed, and then there is this part which is moving. So apparently, this is where the MHC is. That region seems to be moving, seems to be correlated with this, but you need to look at the cross-correlation map. And again, of course, things are more meaningful when you look at this mode shape. So again, you can select any of the first 20 modes, or you can select the fast modes, and you can see the profiles. We call them mode profiles as a function of residue index. After a while, when you start to do this type of analysis, whenever you see a mode profile, you start to make guesses about some design principles about, that is certainly an important residue, you can say, bridging between a region that moves in one way and another. So what is this particular residue? You may start to interpret their behavior. So I summarize before the break. We have a structure, we map it into a network representation and generate the Kirchhoff matrix. And then we focus on the mean square fluctuations, which is given by the inverse of this Kirchhoff matrix diagonal elements, or the off-diagonal elements were the cross correlations. We can decompose this into a series of modes, and then we can generate the profiles corresponding to individual modes. So the mean square fluctuation is a sum of all modes, okay? But now these are the individual contributions. Here's the recipe. It's a summary of everything I've explained so far. And we don't just a repetition. You build the Kirchhoff matrix, you decompose it, eigenvalues and eigenvectors. The eigenvalues, they scale with the frequency squared. They are proportional. The eigenvector is the mode shape that I mentioned. And the eigenvector itself in the GNM is an n-dimensional vector, and it gives you the size of the motion of each residue. The ith element of this vector will correspond to the ith residue, how much it moves along that mode. Eigenvectors are normalized. These are like directional vectors, and they are each multiplied by the eigenvalues, which give the size of the motion. The square of the elements, if you take the square of the elements of the eigenvectors, they give you information on the mobility on that mode, etc. So that ends this part of my lecture. Okay, we'll stop here and give a 10 minutes break.